In mathematics, there are several logarithmic identities. Trivial identities. Note that logb is undefined because there is no number x such that bx equals 0. In fact, there is a vertical asymptote on the graph of logb at x equals 0. Cancelling exponentials. Logarithms and exponentials with the same base cancel each other. This is true because logarithms and exponentials are inverse operations. Both of the above are derived from the following two equations that define a logarithm. Substituting c in the left equation gives lob equals x, and substituting x in the right gives logb equals c. Finally, replace c by x. Using simpler operations, logarithms can be used to make calculations easier. For example, two numbers can be multiplied just by using a logarithm table and adding. The first three operations below assume x equals bc, and, or y equals bd so that logb equals c and logb equals d. Derivations also use the log definitions x equals blob and x equals logb, where, and are positive real numbers and both are real numbers. The laws result from cancelling exponentials and appropriate law of indices. Starting with the first law, the law for powers exploits another of the laws of indices. The law relating to quotients then follows. Similarly, the root law is derived by rewriting the root as a reciprocal power, changing the base. This identity is useful to evaluate logarithms on calculators. For instance, most calculators have buttons for lane and for log 10, but not for log 2. To find log 2, one could calculate log 10 lane, which yields the same result. Proof. Let then take on both sides, simplify and solve for since, then this formula has several consequences, whereas any permutation of the subscripts 1, for example summation, subtraction. The following summation, subtraction rule is especially useful in probability theory when one is dealing with a sum of log probabilities. Note that in practice and have to be switched on the right-hand side of the equations if. Also note that the subtraction identity is not defined if since the logarithm of 0 is not defined. Many programming languages have a specific log1p function that calculates without underflow when is small. More generally, where assorted in descending order, exponents are a useful identity involving exponents. Inequalities based on both are pretty sharp around x equals 0, but not for large x. Calculus identities. Limits. The last limit is often summarized as logarithms grow more slowly than any power or root of x. Derivatives of logarithmic functions where, and integral definition. Integrals of logarithmic functions. To remember higher integrals, it's convenient to define where as the nth harmonic number. Then, approximating large numbers. The identities of logarithms can be used to approximate large numbers. Note that logb plus logb equals logb, where a, b, and c are arbitrary constants. Suppose that one wants to approximate the 44th Mersenne prime, 232,582,657 To get the base 10 logarithm, we would multiply 32,582,657 by log 10, getting 9,808,357.09543 equals 9,808,357 plus 0.09543. We can then get 109,808,357 times 100.09543, 1.25 times 109,808,357. Similarly, factorials can be approximated by summing the logarithms of the terms. Complex logarithm identities. The complex logarithm is the complex number analog of the logarithm function. No single-valued function on the complex plane can satisfy the normal rules for logarithms. However, a multi-valued function can be defined which satisfies most of the identities. It is usual to consider this as a function defined on a Riemann surface. A single-valued version called the principal value of the logarithm can be defined which is discontinuous on the negative x-axis and equals the multi-valued version on a single branch cut. Definitions. The convention will be used here that a capital first letter is used for the principal value of functions and the lowercase version refers to the multi-valued function. The single-valued version of definitions in identities is always given first, followed by a separate section for the multiple-valued versions. Lane is the standard natural logarithm of the real number r. Log is the principal value of the complex logarithm function and has imaginary part in the range is the principal value of the arg function. Its value is restricted to equals at and 2. The multiple-valued version of log is a set, but it is easier to write it without braces, and using it in formulas follows obvious rules. Log is the set of complex numbers v which satisfy v equals z. Arg is the set of possible values of the arg function applied to z, when k is any integer. Constants. Principal value forms. Multiple value forms, for any kn integer. Summation. Principal value forms. Multiple value forms. Powers. A complex power of a complex number can have many possible values. Principal value form. Multiple value forms, where k1, k2 are any integers.